All right, so for this next video, we're going to talk about the mean value theorem, and this is the last section of Unit 5. So I figured I'd start you guys off, or finish you guys off a little bit easy with this unit. So you guys are going to have your test on Friday, and I'll give you guys 2 days of review. And I know I've been pretty bad about posting the solutions to the problem sets, but I'll go ahead and see if I can get that done tonight, which is Tuesday. So as far as the mean value theorem is concerned, it's just a pretty simple definition. It just says that if a function f is continuous over the interval, and I should have said maybe closed interval from a to b, and differentiable over the interval a to b, right? So it has to be both continuous and differentiable. Those are the two conditions for you to be able to use mean value theorem. Then there exists a point C within that open interval where the instantaneous rate of change equals the average rate of change over the interval. So I've given problems like from Unit 2 to kind of get you guys, using this where you have to set the derivative equal to the average rate of change and see where that works. But here in the mean value theorem, we're kind of getting into a little bit more in depth with that. So just to give you guys a basic understanding, let's say I had a graph over here. All right. And I'm just going to go ahead and draw maybe, let me guys the most basic examples like a cubic function, like that. All right. So if I had this cubic function, and let's just pick, let's pick 2 points. Let's say I pick this point right here and that point right there. All right. So this will be my interval from A to B. Well, as you can see, it is continuous. You can just visually tell. And it's also differentiable because I don't really have any, asymptotes, or I don't have any, pointy parts of the graph or cusps or anything like that. So we're good there. So essentially, let's just say I drew a line through those points. That's going to represent the average rate of change. Probably pick a different color. So I have this right here, and that represents the average rate of change. Essentially, what the mean value theorem is telling you is that if this is the average rate of change between A to B and it's continuous and differentiable, then there has to be some other point where the instantaneous rate of change, right? That's basically the slope at a specific point or at a tangent. All right, there has to be some other point on this curve where that rate of change or the slope of a tangent line is the same as that line right there. So it's almost like, picking another line that's parallel that's on that point, maybe like right there. Hopefully that comes out parallel. That's a little bit crooked, but you kind of get the point. In fact, there are actually 2 values here. So we'll call this like maybe C2 because I know that's coming up later. And then this one right here, this is also parallel to that line and it crosses that point. Let's see if I can not screw this up. I totally missed it. Pretend that's touching that point. All right. And that point, this point right here, C1. So we have 2 C values where the instantaneous rate of change equals the average rate of change between that interval. All right. And that's pretty much what the mean value theorem is telling us. So let me go ahead and let's work out this first example, and it's kind of breaks it up into 2 parts. It says use the function f of x is equal to negative x squared plus 3x plus 10 to answer the following. So on the interval from 2 to 6, what is the average rate of change? Well, that's easy. We just got to do the f of b for the average rate of change, f of b minus f of a over b minus a. So if we plugged in 6 into this, I'll have negative 6 squared plus 3 times 6 plus 10, all divided by 6 minus 2 is 4, right? I forgot to plug in the 2, of course. So all of this minus, and I plug in 2 into that, I'll have negative 2 squared plus 3 times 2 plus 10. And that's equal to, let's see, negative 36 plus 18 plus 10 minus, that'll be negative 4 plus 6 plus 10, all divided by 4. And let's see, that'll be, trying to do this in my head, negative 20 over 4, so it's equal to 5. Kind of ran out of space there. That was really sloppy, but you get the point. We know how to do average rate of change. All right. Now it's saying on the interval 2 to 6, right, when does the instantaneous rate of change equal the average rate of change? So as far as instantaneous rate of change, you should remember that that's referring to the derivative or the slope of a tangent line. So we're going to go ahead and figure out what the derivative is. So I have f prime of x is equal to negative 2x plus 3, right? And then we're going to go ahead and get that and set that equal to, that should have been negative 5, sorry. So we're going to get that and set that equal to negative 5. And then you'll end up with negative 2x is equal to negative 8, x is equal to 4. All right, so for this next problem, it's going to tie in a couple of things as far as intermediate value theorem and mean value theorem, so you can kind of know the difference between the two. It says a hot air balloon is launched into the air with a human pilot. The twice differentiable function h models the balloon's height measured in feet at time t, measured in minutes. The table above gives the value of h of t and the vertical velocity v of t of the balloon at selected times t. So if t is between 5 and 20 minutes, must there be a time t when the balloon is 50 feet in the air? Justify. So there's probably a long process to answer these questions as far as justifying all of this, but I'm just going to keep my answers short, and if you want to keep them short for the problem set, I'm totally fine with that. But essentially for this one, if there's a specific time t when the balloon is 50 feet in the air, they're not really talking about rate of change or instantaneous rate of change or anything. They just want to know if there's a value c in between this interval where you'll have where you can get a balloon that's 50 feet into the air. So for that one, you really only have to go back to what the intermediate value theorem is. And if I look between 5 and 20, well, if you see right here, if you're going from 40 to 70 and this is a continuous function, the fact that it says twice differentiable means that it's automatically continuous. So you can tell that if you're going from 40 to 70, there has to be a value in there at least once where you're at 50, right? So I'm just going to go ahead and keep the answer simple and say yes because of the intermediate value theorem. All right, I'm just going to try to keep this video short, so I'll just leave the answer like that. But now for this next part, it says, for 20, if t is between 20 and 30, must there be a time when the balloon's velocity is 1.5 feet per second? Justify. Now for this one, we're talking about the velocity, and we know that that's the velocity is the average rate of change for, with respect to position. That's the derivative of the position. So for that one, we can actually go ahead and find out what is h of 30 minus h of 20 divided by 30 minus 20. And if we go ahead and plug that in, well, we have, let's see, h of 30 is 80, h of 20 is 65, divided by 10, and we do end up with 1.5. So pretty much, yes, we can. Yes, we can justify this because of the mean value theorem. I put IVT for this one, but I'm actually spelling it out. You could have just said MVT, but whatever, I'll just write it out. All right. So yeah, if the average rate of change between those 2 points is 1.5, then there has to be another time t where the balloon's velocity or the instantaneous rate of change is 1.5, and that's just based off of the theorem that we were describing earlier. So again, nice short lesson. I can't see this problem taking you too long, so that way it gives you a little bit more time to work on those optimization problems, because I did give you a lot for that. So just make sure you practice adequately. I'm going to post a review hopefully by tonight, if not by tomorrow in the afternoon. And yeah, you guys should be ready for the end of Unit 5, and soon we're going to start the very last thing that they have to learn in Calculus AB, which is integrals. So hopefully this helps. Take care.